What is rotational positional embedding? And how can we utilize this for higher dimensional data encoding? Let's first dig into what rope is. In modern language models, an item's absolute position is less important than its relative position. To put it simply, knowing a word is 3 words after another is more useful than knowing it is the 157th word in the document. By encoding its positional information through rotation, rotational embeddings create a symmetry function that operates similar to pure mathematical functions. A 2D visualization shows how this is done by retrieving the inner product and relative distance from the blue and red positions as they rotate around a vertex. Relative distance is the straightforward difference between the 2 position values. Vector distance is created by rotating a base vector by an angle equal to the product of its position and theta. The inner product is the dot product of the 2 rotated vectors. The main contextual compression powerhouse is the optimization of the use of quaternions to extend rope mechanics into 3 dimensions. The z-axis can represent a compressed summary of parallel data streams. This is because inherently quaternions are 4-dimensional numbers encoded into 3-dimensional space. Through clever optimization techniques and parallel processing structures with global updates, the encodable dimensions offset space with time in a way that scales proportionally to hardware and enables parallel offloading that maintains end-to-end security. The core insight of rope is that the inner product, a measure of similarity, depends only on the relative distance between 2 points. We can apply this exact same logic to distributed systems by making a simple substitution: replace position with time. In a conflict-free replicated data type, CDRT, we don't care about when an operation was created in absolute, universal time. We care about its relationship to other operations. By encoding an operation's timestamp into a rotation, we gain similar benefits to rope in language models. The total merged state shown by the purple vector demonstrates the merge process of vector addition in a commutative and associative way. The simulation visualizes a last right wins CDRT pattern using rotational state vectors. The key idea is that the total, convergent state of the system is the vector sum of the latest known operation from each agent. At any given moment, each agent has a latest operation which has a value and was created at a specific time. This operation is converted into a 2D vector using the same rope formula as before. In the diagram, the colored lines represent the latest vector for each agent. As an agent submits a new operation, its value and time change, causing its vector to point in a new direction and have a new length. The interference graph visualizes the same data, but as waves, showing how each agent combines. The global state wave in purple shows the sum of all individual agent waves. Be sure to check out the GitHub for the full interactive course.